the next step in the evolution of Cirrus Aircraft, the jet was natural.
Welcome to Cirrus Aircraft and the Cirrus Vision Jet updates. We're going to do things a little bit different for this update. We're going to bring the engineers to the airplane and actually show you what we've been doing the last several months and give you a peek at what we've got coming up ahead. We're going to start with Paul Bray, Vice President of Product Development. Paul's been with us for 15 years, starting on the SR-20 with us. He's going to show you what we've been doing on the airplane.
I'm pretty excited to be here and talk about the airplane a little bit and about the program. This has been a pretty good year for us. We made a lot of progress in 2010. We intend to make a lot more in 2011. We've got some 350 flight hours on this airplane now. We call it V1. This is the airplane that we've used to validate the performance and the stability and control. This year alone, 128 flights. That's some 2.5 flights a week. I would call that an active flight test program. An area where we made some big progress this year is right here. This is where the parachute's going to come out of the airplane. In August last year, we did prototype testing on a scaled parachute, and we've characterized the performance of that parachute, and we are ready to move ahead with the recovery chute that you'll see coming out of there on the future airplane. Some other places that we've made some progress this year, we redesigned the inboard wing loft, and we validated it using computational fluid dynamics at this point. It's pretty exciting, actually. We think we've taken about 20 drag counts, about 9 knots improvement in speed on the airplane, and of course that improves range. In addition, we've characterized the rest of the wing performance here. To improve the roll control and crosswing control, we're looking at extending the aileron span a little bit, and we will bring it out into the tip and redesign the tip a little bit. In addition, we've increased the chord on the trim tab, which improves the pitch performance and gives us a lot better landing performance at this point. So we've made a lot of changes to the airplane. We think we have the type design set for aerodynamics and performance. And the next thing we're going to do is we're going to have our chief engineer, Dave Rathman, come out and talk about some of the systems improvements we've made on the airplane and where that design is going.
Hi, I'm going to tell you a little bit about the areas of interest that we're working on with our V1 test airplane. Some of the things you can see on the outside of the airplane. Some of the things are on the inside that are kind of hard to show. We're looking at ice buildup on the nose, or ice accretion, and we're also looking at it on the windshield. We've iterated the design of the ice delivery device here on the nose. We have a TKS delivery system that secretes fluid on the nose, and we also record that for playback. For test purposes, we'll test with and without the flow on the TKS to see how ice builds up and sheds on the nose. We have the nose painted black on the test airplane. We've also got grid lines painted on it so that we can see the areas of buildup. We have a camera here so that we can monitor that buildup real time in flight, and we also record that for playback. We also have ice protection for the windshield. On the top here we have a spray bar. It's not mounted flush on the test airplane so that we can iterate its design, moving around and changing its width to alter the flow patterns on the windshield. And to date, we've got a pretty good dispersion pattern that will keep most of the windshield clear on both sides of the windshield. We've also got a heated engine inlet. This one's electric so that we can vary the heat output in various different areas. It's also black with the white grid lines painted on it so that we can evaluate the buildup characteristics. The production airplane will be heating that with bleed air. Another area of interest on the test airplane is the wingtip. Here we have some interesting instrumentation. Out here on the tip we have a high-definition camera that gives us a field of view from the nose to the tail. We can watch ice build up on the nose and windshield, and we also, it's a high enough frame rate where when ice sheds or releases from the airframe, we can monitor the trajectory over the top of the airplane. A particular area of interest is making sure that shed ice flies clear of the engine inlet. Also over here we have these two gauges. One of the things that's important to know when you're flying in ice and evaluating the performance of our ice protection systems is both the rate that ice builds, or ice accretion rate, and also the droplet size. This little ball here we use to quantify the ice droplet size. Larger droplets of vapor or water will build ice in larger diameters, and smaller droplets will build ice in a smaller area. And we can watch the characteristics of that in flight through the video camera, and we also have heaters in there where we can release it and do another test point. This gauge here is the Vernier Ice Accretion Meter, or VAM. This has a very specific shape on this bar that builds ice in a known characteristic, and based on the size of that ice, we can look at this Vernier meter through the camera and see the thickness of that over time. This also has a heater in it that we can release those ice shapes and start additional test points in flight. To date, we've actually flown 4 different flap configurations on V1. This is nearly the final configuration. The things that we're particularly interested in flaps is getting a good stall speed, reasonable drag characteristics, and a low weight and low complexity design. We've derived this design that has a hinge below the wing section, or a drop hinge like we like to call it, and a multi-element flap. As you can see here, we have a small vane that's attached to the main flap body, and it helps to keep air attached to the flap at larger flap deployment angles. Again, on the test airplane, you can see that we have these releasable egress doors that will release in flight in an emergency. On the production airplanes, we'll have a 2-piece lower air stair door, clamshell door. Recently, we've completed some full-scale pressure vessel testing where we've pressurized the fuselage section to limit pressure, and we're starting to evaluate door seal design, details, and door latching mechanism. In addition to flight testing our V1 test airplane, our engineers are also very busy with detailed design on the airframe, systems, and systems integration. To talk a little bit more on flight testing, I'd like to introduce Chief Flight Test Pilot Mike Stevens.
Thanks, Dave. Had a lot of unique and interesting flights since we talked last October. Been beaming up and down the East Coast doing some marketing, as well as a lot of interesting engineering flights. Been able to operate our V1 prototype in a lot of different weather and through a lot of different airports. East Coast, very interesting to fly the personal jet in a real world environment, getting out of the traffic pattern. So flying the SF-50 prototype in many respects is very similar to flying a Cirrus SR-22, which I've been privileged to fly with for over 10 years now. Getting in the SF-50, once you're strapped in, you can tell ergonomically it's a Cirrus, and then from there on, some of the differences are quite interesting. Starting the engine, there's nothing to it. It's all FADEC controlled. Just hit the key, count to about 10, and it's up and running. Once the engine's spooled up, get your generators online and start taxiing. We use the cast-ring nose wheel on the SF-50, similar to the SR-22. The SF-50 actually has a centering mechanism on the nose wheel that makes it a lot easier to keep going in a straight line and requires a lot less brake action than you would find in the SR-22. Getting out to the runway, you can feel the trailing link landing gear. It's a smooth ride, it feels solid, it feels like a more substantial airplane. Once you're at the hold short line and ready to go, when you advance the throttle, you'll find that not having a propeller is actually a really nice thing. The airplane accelerates straight down the runway, and at about 75 to 80 knots, when you think it's time to fly, you rotate, pitch up to a similar attitude that you're used to in the SR-22, gear up, flaps up, and you're on your way uphill maybe at 2,500 feet per minute. 18 minutes later, you should be at about 28,000 feet, set your cruise power, and away you go. It should be 300 knots and kick back with the autopilot on, listen to some music. Terminal environment, if you want, you can fly it fast or you can fly it slow with the SF-50. Our VMO is about 250 knots, so if you go charging into an unfamiliar area, things can happen pretty fast. In the traffic pattern, the SF-50 is great. You can slow down maybe 120 knots on downwind, 100 knots on base, about an 80 knot final. So once you're established on final, it's a very similar sight picture as you would see in the SR-22. Landing the airplane is no problem. Touchdowns usually about 65 knots, and it's very easy to operate out of a 3,000-foot runway. We tend to operate this airplane fairly heavy because of all the test equipment in it. We've been pleasantly surprised with our ability to get in and out of short fields. And I think that'll carry through to the end user. I believe that the 75 to 85 knot final will be manageable for most of our customers.
Thanks for spending a few minutes with us today. As you can see, there's a lot of exciting things happening here, both on the VisionJet and throughout the company. So look forward to seeing you again soon on our next Vision Update. Thank you.